Hello, students of AP Chemistry. This is going to be section 1.2 on mass spectroscopy of elements. Mass spectroscopy, or sometimes called mass spectrometry, is a elemental analysis method that is very good at identifying the type of substance that you have if it is unknown, and also showing you the relative proportions of the different isotopes of that substance. So our learning objective for this is to explain the quantitative relationship between the mass spectrum of an element and the masses of the element's isotopes. So say you're working in a laboratory and then you have this sample here, this gray powder, and it is unknown. But what you do know about it is that it's a pure substance. So you want to use some sort of analytical technique to figure out what this substance is made of. And mass spectroscopy is a very good method to do this. So if we see here, this is what a mass spectrometer looks like. It's a big desktop instrument. But what's going on inside is very interesting, but also kind of complicated. So you're generally going to make a solution of your substance. You're going to mix it with water or something else that it dissolves in. And then that's going to be fed through here. Here's where the sample enters the machine. And then it is heated and vaporized by this coil, and then it is bombarded with a beam of electrons. The point of the electrons is to ionize the gas particles. And that's going to be important later because those ionized gas particles are then accelerated further down the tube where they come in contact with a magnetic field. And that's important because if those particles weren't ionized, they wouldn't really have interacted with the magnetic field unless they were sort of magnetic metals to begin with. But since they are ions, since they are charged, they will interact with the magnetic field. You might not know this at this point in your science careers, but electricity and magnetism are sort of two sides of the same effect. So magnets have a big impact on electronics and vice versa. So as we have our ions, our charged particles, flying through this magnetic field, they will start to get deflected by it. So an analogy I kind of use for this is say you have a heavy bowling ball and a light bowling ball, and you both kind of roll them in the same direction. And say there's somebody kind of along the path of that is trying to kick those bowling balls as it passes by their feet. Say they kick the heavy one, it'll be bumped a little bit, and say they kick the light one, it'll be bumped a lot because something with a lighter mass is easier to deflect its path. And the same thing happens here. As you have heavier ions, they're going to be deflected kind of lightly, and then lighter atoms are going to be deflected pretty severely. And as they are deflected in this path, they're going to hit a detector at sort of the end of the tube. And there's a film on here that sort of detects when a charged particle hits it. And then the detector is going to be counting how many times charged particles hit certain parts of that film. And that'll give us a good idea of the relative masses of the particles that are being sent through the instrument. And then you're going to end up with something like this. So this is called a mass spectrum. And it's a graph where on the x-axis we have the mass number of the substance. And then on the y-axis we have the relative number of atoms. So basically what the software was counting as different hits for different relative masses. So if we kind of analyze what we have here, it does say at the bottom of this graph mass spectrum of silicon, and that's kind of a spoiler here because we want to figure out why this is silicon based off of the graph itself. So you'll see here that the largest peak with a relative abundance of 92.23% corresponds to a mass of 28. And if you look at the periodic table, you'll see that silicon, atomic number 14, has a mass number of 28 due to the fact that silicon has 28 protons, sorry, not 28, 14 protons and 14 neutrons. And what we end up seeing here is one big peak at 28, which is closest to the average mass of silicon. But we also have a peak at 29 and a peak at 30. And this is a good representation of the natural abundance of isotopes of silicon. If you don't recall what an isotope is, but isotopes is basically sort of like the relationship between particles of the same element that have different masses. So if we consider silicon, for example, silicon has 14 protons and will always have 14 protons. Anything with 14 protons is silicon, and anything without 14 protons is not silicon. Remember that the number of protons literally defines the element. However, an atom of silicon does not need to have the same number of neutrons. And that's what we see here, because we have our common silicon, our silicon that shows up the most in the detector, has a mass of 28, which means that has 14 neutrons. But we also get a peak at 29 and a peak at 30, which corresponds to 15 and 16 neutrons, respectively. But you'll see that these peaks are not as large, and that actually says a lot about the isotopes themselves. Because if any one sample of silicon is going to be mostly mass of 28, that tells us that silicon with a mass of 28 is more stable and more preferable in the laws of physics and the laws of the universe. And what I mean by that is, like, if you think about the nucleus of an atom, it has protons and neutrons. We're going to continue to talk about this in the next few lessons, but the neutrons are sort of holding those protons together, and that has a relative stability. And the more unstable that nucleus is, the more likely it is to undergo nuclear decay, which means that the atom splits up into smaller atoms and kind of goes away. So this is telling us that the silicon 28 is the most stable because it is the most abundantly found one in nature. The 29 and 30 are a little bit more unstable, so they're more likely to fall apart, and you won't see as many of them naturally occurring. So what we can do with this is we can also use these relative abundances in percents, so to sort of calculate what the average mass of silicon is, and that's usually what's represented on the periodic table under each of the elements. The atomic mass that is represented on the periodic table is often something with a non-whole number, and that's because you're getting a weighted average of all of the isotopes. Because remember, you can't have like a fraction of a particle. You can't have a fraction of a neutron. So the fact that on the periodic table it's 28 point something for silicon tells us that the larger isotopes, the 29 and the 30, end up bringing that average up just a slight bit. But we can calculate what that number actually is by using sort of the weighted average method of taking each of the data points, so 28, 29, and 30, and multiplying them by their percents as decimals. So the one that was 92.23%, we multiply by 0.9223. The one that was 4%, we multiply by 0.0467. If you're confused about how to get the decimal, just take that percent and divide it by 100, and that will give you the decimal form of the percent. And then we add all of these together. So the sum of these three data points ends up giving us 28.1, and that is closest to the actual average mass of silicon that we see on the periodic table. And remember, if we're using this with units, it'll either be 28.1 AMU, atomic mass units, or 28.1 grams per mole. And that is it for this topic. Mass spectroscopy can get a lot more complicated, and hopefully if you study science in college, you'll see more examples of how mass spectrometry can be used to not just identify single elements, but the structure of compounds as well. But this is all we are going to be worried about for AP chemistry in particular. So I'll see you in the next one.